Thank you everyone for joining us tonight for what is the final lecture in our winter series. And tonight, we're really fortunate to have Professor Richard Worden. Richard is a professor of geology at Liverpool University. He studied geology and geochemistry at the University of Manchester, where he also did his PhD. He has published more than 160 peer-reviewed papers. He supervised nearly 40 PhD students and has taught modules on petrophysics, carbon capture, basin analysis, sedimentary geochemistry, hydrology, and has led field classes all over the UK. He's been undertaking research in carbon capture and storage for more than 20 years. And tonight, he's going to give us his lecture, The Geology of Carbon Capture and Storage, why we need it, what it is, and what is holding it up. So before I just hand over to Richard, could I ask people to mute and to turn off their videos so we have an enhanced broadband for Richard. And with that, I'll hand over to you, Richard.
Thank you very much, Richard, and thank you for that introduction. It's always interesting hearing yourself, your life history. Sometimes it seems like a very rapid series of events, and other times it can seem like a very long time. Just meeting John Pollard online, it felt like a long time. John taught me as an undergraduate in Manchester between 1981 and 1984. And that does now feel like a really long time ago. Anyway, I'm going to talk, as Richard has introduced, about the geology of carbon capture and storage. I'm going to give my own flavor on this. I'm going to set the scene, talk about why we need it, talk about the risks, and then talk about the types of things that might happen when carbon dioxide is injected into the deep subsurface. The little graphic there I'm going to show again, it's just illustrating the range of scenarios that geologists have considered for injecting CO2 into the ground for permanent storage. I'll talk about that more in a few moments. So we wouldn't be doing carbon capture and storage if it wasn't for the issue of climate change. And it's a modern problem, but it's got roots embedded in the recent past. And by that, I take us back to the Industrial Revolution, and it's an accelerating problem. So there's a couple of graphs on the screens in front of you. The lower one in the right gives you temperature as a function of time going back to 1880. And we don't need to worry about where these temperatures have come from. They're probably very well measured temperatures, actually. There is a degree of cyclicity over a short number of years. And then you can see there's a red line that's smoothing that out. And you can see there's peaks and troughs. But there is an inexorable...
No graphs, I'm afraid.
Sorry.
Again, sorry.
Richard, I think you need to share your screen.
Oh.
It hasn't come up.
That would be rather useful.
Yeah, I thought it was an introduction you were giving, but then I realised.
Well, it is effectively. Can you see my screen now?
Yes, that's it. Yeah.
Very good. Very good.
Yeah, that's it now. Okay,
so we have an inexorable increase in temperature with time, and that is matched by, well, we're going to see what that relates to in a few minutes. Over the last couple of thousand years, the temperature's been broadly stable, although it looked like we were entering a very mini ice age, a small ice age in the Middle Ages. And then that has been completely reversed by a relatively rapid and extreme rise in temperature. So what is the problem with global warming? I know there's some people around the UK who look forward to temperatures, for instance, similar to southern Spain. That's what they think is going to happen. And every day will seem like a holiday on the Costa del Sol. Well, that is going to be the least of anyone's experiences. Problems of global warming increase things like increasing sea level due to land ice melting, flooding of low-lying regions, which means cities, loss of essential farmland, saline inundation of coastal aquifers. So basically, there'll be nowhere for people to live, there'll be no farmland, and the groundwater will be contaminated and useless. There will be increasing storminess. There will be wave and tide damage in coastal areas, river flooding, wind damage. And changing ocean circulation patterns will lead to the risk of localized cooling. And if the Gulf Stream switches off because there's no more ice melting in the Arctic, that means Northwest Europe, ironically, may get colder. So Britain may end up getting colder, even though the whole globe is getting warmer. Just go out of that. So what is the origin of this problem? So we have increasing atmospheric CO2 concentrations, and this has been monitored by looking at tiny bubbles of fluid in ice going back many, many thousands of years, at least 12,000 years before the Common Era, before this time, 14,000 years before the present date. And we can see, I remember as an undergraduate, it was said that the global CO2 concentration was somewhere less than 300 parts per million. Now, we studied that because we wanted to work out what the acidification of rain would be, and that depends partly on the CO2 concentration of the atmosphere. And then you can see now the values are 400 ppm and ever increasing. Now, you could say, well, that's just a coincidence, isn't it? Well, then you can compare it to the global temperature scale over a similar-ish period. That's 2,000 years. So those two time periods are roughly the same. And you can see there's an incredible matching of the rate of increase. And there are mechanisms that can be put in place to explain that as well. So this isn't just pattern matching. There is hard physics and chemistry to go behind that increase. So what has happened to increase our atmospheric CO2 concentration? Well, we can look back to the Industrial Revolution and the mass burning of fossil fuels. So burning a few logs to stay warm from the Stone Age period right through to before the Industrial Revolution would have had very, very minimal impact. But then when we started burning coal, well, there's also an incredibly rapid growth of population. Burning coal started to put very large quantities of CO2 in the atmosphere, and then that has gone up ever since the Industrial Revolution and has accelerated through the second half of the 20th century and is slowing down a little bit, but it is still going up. And you can see the emissions by region, and Europe is by no means the worst offender. That's the European Union. Well, this was before the Brexit happened, so that would include us. And you can see China and United States are culpable of very large quantities of CO2 release. So that's history. Now, we need to think very carefully about this because there's some people who think simply by buying an electric car, that will solve all the problems. Now, the sad fact is that's not true at all, because if you buy an electric car, we still have to have electricity generated somewhere. Now, you might say, well, let's have more alternative energy. Let's have more wind turbines. Let's have generate their turbines in, for instance, estuary channels. We could have one in the Mersey Channel. It's got a very rapid flow rate between Liverpool and Birkenhead. Well, that's true, but we need to distribute that electricity and we need batteries. So we're just moving the problem along a little bit. This graph here is on the left-hand side is very meaningful as far as I'm concerned. So direct emissions means burning fossil fuels, and then the CO2 that's produced is simply emitted to atmosphere. And you can see transport is almost all direct emissions with a very small amount of the reddy brown color, which is generated from electricity, which could be produced by burning fossil fuels, of course. So you can see this, the big blue bar here, this is direct emissions from agriculture, forestry. This is direct emissions from industry. This will be things like cement manufacture, steel manufacture, other energy sources, buildings, that's making buildings and keeping buildings warm. Now, if we simply move on to electric cars, all we're going to do is change that one to largely, hopefully, brown or whatever the color is, so long as we have green generation of electricity. Now, that will make a big difference, but it's not even a quarter of our generation of greenhouse gases. We need to think very widely about all our lives, including, this is very unpopular with our current government, demand for never-ending economic growth. That is our dominant economic model. No one seems to be able to get away from that, but that will destroy us in the long run because we can't have never-ending economic growth. It is literally impossible and it is unsustainable. We also have a growing global population, which is also unsustainable. Now, in Britain, the population is roughly stable, but there are some parts of the world where populations are growing very rapidly still, and that is a problem for all of us. We have an ever-increasing demand for energy as our lifestyles change. We have tablets, we have mobile phones, we have computers all over our houses, we have flat-screen TVs in many rooms. these all demand electricity, which currently a lot of it is producing greenhouse gases. We also have increasing demands for goods. You see the size and scale of the shipping that comes to the Suez Canal when it was blocked. It's staggering. That has to be made. That requires plastics. It requires energy to generate power for the factories. We have increasing urbanization, which means more concrete and steel manufacture, and making concrete releases vast amounts of CO2. Same for steel. Now, you're probably familiar with the arguments going on at Whitehaven and the deep mine that's planned. Well, one of the objections is that the manufacture of steel needs coal and it will release CO2. I'm not saying I'm supporting that, by the way. I think UK generation making its own steel is a very good idea. And we have ever increasing demands for CO2 intensive food products, and that is especially meat. Very unpopular with the avid carnivore, although it's less of a problem for vegetarians in terms of the amount of CO2 that's produced. So what is our history of fuel and power? So I entertained myself by putting this together, actually. So if you look back into the Stone Age, people used to burn wood for food, for warmth, and then relatively early for manufacturing metals, your bronzes and your tins. But also we had animals, which were power, to source of power. So if you think of any oxen pulling a plow, that is animal powered, and that's powered by plants. Water wheels, we know what generates those. I was at Style Mill only a few weeks ago, reflecting on that water power that was needed to provide energy for Style Mill south of Manchester. Windmills, wind sails on boats. This is where we used to get our energy from. And then all of a sudden the Industrial Revolution came along. Mining was invented largely in the UK, of course, and we started producing lots of CO2 when we burnt our coal. And then oil and gas came along, especially in the 20th century, and the UK finally caught up in the mid-1970s, I guess. And then we moved on to nuclear, which was wildly unpopular when I was an undergraduate in the 1980s in terms of the environmental movement, and is now, strangely, being brought in from the cold because it doesn't create greenhouse gases. And then we can look to the future. Now, hydroelectric isn't exactly new. Most of Norway's electricity comes from hydroelectric power, for example. But if you're a flat country like the Netherlands, then it's not very useful. We have wind turbines. We're all familiar with those all over our coastlines, many parts of the country. In very large quantities of electricity can be generated when there's a wind. And solar, of course. Solar is good, especially, for instance, if you live in Morocco or southern Spain. Not so good if you live in Iceland in the winter. But there again, move on to the next one. They've got geothermal energy. And the UK is beginning to try to exploit geothermal energy. We suffer in comparison to Iceland because the rocks don't get that hot, that near to the surface. But there are areas with high geothermal gradient, and they are being exploited. I was reading about a geothermal well being drilled in the Eden project in Cornwall just this morning, actually. And then we have tidal power. Now, we are a coastal nation. We have estuaries, we have channels with incredibly consistent and high energy currents that flow in and out, but we don't really exploit them because there are environmental issues with all of them. Now, that's what we have now. My wife, who sat downstairs working, she's an engineer and she is inventing new materials. And I guess there's a hope that a lot of people have in their hearts that there'll be some brand new technology that no one's ever thought of. Now, that won't be geologists who come up with that, I'm afraid. I think it'll be more people in the engineering and physics realm. So, in terms of the brief history of fuel and power, where are we today? So this is a graph of where energy came from. This is for the UK as a function of time, going from 1900 through to nearly 2020. And you can see coal was the vast majority of the oil energy production, and then oil came in and gas, and then we got little bits of nuclear steady from the roughly the mid part of the 20th century onwards, and then wind, geothermal and solar creeping in. And you can see coal is leveling off, if not now precipitously dropping, because there are no new coal-fired power stations, and the ones in existence are being rapidly decommissioned. But what does the future hold for us? So again, we can go back to 1995 and step forward in 5-year steps. Now, this is a prediction because this looks into the future. Now, many people do this. So BP is especially good at providing what it thinks the future holds, and they're widely respected, and it is useful because it informs investor decisions, of course, but governments have a big interest in this as well. So the USGS looks at this, the British Geological Survey does as well. So that in the future, it is expected that coal drops very much. it is expected that gas holds its own, and gas is relatively good as a greenhouse gas emitting fuel because it doesn't make that much in comparison to coal and oil. And you see oil in terms of electricity generation is disappearing very quickly. We have nuclear, which we hope is holding steady. That requires new power stations to be built. We have hydro, which is roughly steady as well for the UK. We don't have that much opportunity, also we think. And then we have wind growing and we have solar growing, which relies on new technology. My point for showing you this is that we're going to be burning fossil fuels in the UK for at least 30 years and probably a lot longer. And that will be the same for the whole world. So if we're still burning fossil fuels, we are still emitting CO2. So we need to do something about that, unless we do what some environmentalists want and we instantly stop burning coal, oil and gas and don't use them for a fuel. And given how reliant we are on it at the moment, I shudder to think what the state of the United Kingdom would be. We would have amazing fuel poverty, and that would lead to major social unrest. It's an incredibly difficult problem to deal with in terms of energy consumption, and we need energy. So what do we do? Well, this is where carbon capture and storage comes in, because for many years it's been proposed as the solution to continued burning of fossil fuels. Now, there's a phrase that's crept in, something called the energy transition. You've probably heard of that. And that means we're going to slowly transit from a fossil fuel dominated economy to a non-fossil fuel dominated economy. And CCS, carbon capture and storage, is supposed to be the stepping stone from one technology to another. So this little diagram, it shows you where people think CO2 could be injected. That means offshore, near or adjacent to oil rigs. It could be oil and gas accumulations onshore. It could be associated with aquifers. It could be associated with deep coal mines. There are many, many places it could be injected and stored geologically forever. That's the plan. So I put this together largely for non-geologists, although I thought I'd leave it in just because it's a nice series of pictures and there's some outcrops there we can enjoy looking at. So I gave a talk to a group called the Science in the Snug just before lockdown last year, probably late February in 2020. And it's a bunch of interested people who know nothing necessarily about science in general and certainly nothing about geoscience. So I put this in and I just wanted to let people think about what's in the subsurface. And the two main geological entities to think of are reservoirs or aquifers, depending how you want to think of the fluid in them. And this diagram illustrates a reservoir, and it's got something on top that's impermeable. I'm going to illustrate that. That's the seal. So we have different trap configurations, and this is by analogy to oil and gas geology, and that's because CO2 injection is being planned and undertaken by oil and gas companies, and because it's utilizing exactly the same phenomena in the subsurface. So we have anticlinal structure, we have faulted structures, we have stratigraphic trapping structures. What you have is a porous and permeable rock with an impermeable rock on top. So we've all seen sandstones at outcrop. There are some lovely sandstones in the Vale of Eden, those Permian sandstones and Triassic sandstones at outcrop. Well, this just happens to be from Dawlish in Devon. These are Permian dune sandstones. And in thin section, or this is a scanning electron microscope image, you can see there's lots of holes. And those holes are where either oil or gas or water is stored naturally and where we will store CO2. The corollary to a reservoir, for it to work, is you need a rock on top that is impermeable. So that's called the seal. Some people use different words like cap rock or top seal, but they all mean the same thing. It's a rock on top of a reservoir that is impermeable or has vanishingly low permeability. Again, you've probably seen rocks like this at outcrop. This is also on the south coast of England. This is at Charmouth, just to the east of Lyme Regis. And these are mudstones, very fine mudstones, and they've actually got thin chalk layers in them. But these are effectively impermeable to fluids trying to flow through them from bottom to top. This again is an electron microscope image, and you can see there are no pores in this effectively at the resolution afforded to us by this image. And that tells us that this rock is impermeable and it will hold fluids underneath it. And we know these things work because oil and gas discoveries work. We can have an oil field, we can have a gas field, and they're held in by an impermeable rock, this seal, and they're stored in these natural rocks called reservoirs. So this is an entirely natural phenomenon that we are reverse engineering. So what are the UK's plans for carbon capture and storage? Well, these move very, very quickly. And what's interesting is seeing how increasing quantities of money are being put into this scheme by government and by industry. Large quantities of money are being put in by the EU as well, which we now have limited access to, of course, but there's a very widespread governmental recognition that this needs action, and it shouldn't be left just to companies. In fact, it can't just be left to companies because of the regulatory issue. I was part of a major research project a few years ago that reached culmination with a series of high-graded oil and gas fields that were going to be exploited for carbon capture and storage. And it was estimated that there are at least 574 possible storage sites, and these have enough storage within them to hold 200 years worth of carbon dioxide emissions at the rate of generation from 2016. Now, if we're increasing more CO2 per year, then that duration will drop a little bit. But by then, well, probably we'll have run out of oil and gas, certainly coal, probably not, but then coal is such an evil concept these days for environmentalists. We won't be mining coal for electricity generation by any means. Now, the other thing we wanted to undertake was an acknowledgement that we're going to try and reuse oil and gas infrastructure. And there's a plan to use rigs, repurpose oil wells, and most importantly of all, repurpose pipelines that were designed to take oil and gas from the oil field onshore to refineries. And our plan is to take these old pipelines before they decay or are removed and repurpose them for injecting CO2 along the pipeline and then deep into the subsurface. So we wanted oil and gas fields as close as possible to existing target pipelines. That means pipelines that are now redundant or soon to be redundant because the oil and gas fields have run out of oil and gas. So of those 574, there were 113 that were within 50 kilometers. That was seen as an economic maximum distance to build a spur from the existing pipeline to the CCS sites. And you can see where the sites are. It's basically mapping out the petroleum geology of the UK. There's the Irish Sea, there's me in Liverpool down there. This is the southern North Sea, central North Sea here, northern North Sea, and then we don't look into Norwegian waters, that's outside our jurisdiction. There are also fields to the west of Shetland as well that could be exploited in due course. So this project, the Acorn project, ended up high grading 2 sites. One is the Lower Cretaceous Captain Sandstone, and that's going to take advantage of the Atlantic pipeline. It's really close to shore, and the idea is to reuse this pipeline, stick CO2 into the pipeline and inject it into wells into this aquifer. So this is much bigger than any single oil field. This is the whole aquifer. And in this, there are little pinpricks on the scale we're looking at, pinpricks of oil and gas fields. And we can fill the entire thing. We're not limited to the oil and gas field volumes. We can fill the entire aquifer. That's the plan anyway. We also looked at this aquifer, or this body of rock. This is the May sandstone. It's a Paleocene sandstone. And because it's so vast, we limited ourselves to looking only part of it, and we called it the East May. But these two together have incredibly good attributes for future CCS. And in fact, the hot news is that this one, the Atlantic pipeline and the Acorn site, is going to be used with a well probably drilled towards the end of next year. And that will be the UK's first industrial scale CCS. So what is the benefit of using exhausted oil and gas fields? Well, manifold, but most of all, what's very interesting is we already know what's in the subsurface because people have been drilling wells for 60 or 70 years. We know what's in the subsurface. It's basically free data. We don't need to drill exploration wells to test what's there. We know what's there. Because these structures have held oil and gas in the past, we also know that they can hold fluid and for millions of years, and that's exactly what we want. And there's an assumption that because these structures have held oil and gas, they will also be able to hold CO2. In an old oil and gas basin, we know there are oil and gas pipelines. That's what I've been talking about. So we can reutilize the existing infrastructure. And this is not a trivial issue. Because the UK has been at the forefront of oil and gas geology for so long, there's an enormous fund of technical skills and knowledge from the oil and gas industry in the UK now. Now, as our industry subsides and as oil and gas fields die off, and if the government doesn't sanction any new appraisal wells and developments, then those skills will disappear and we won't be able to do what we can do right now. So there's a lot of reasons to act and to act relatively quickly. So we're going to be injecting CO2 into the subsurface. What is the expected fate of that CO2? Well, there are different things that might happen. And let's start with, so this is time on the y-axis, and this is a logarithmic scale. So that's 1 year, so that takes us to 2022, and that's looking 10,000 years in the future. This is trapping contribution. So if we inject a certain volume of CO2, does it stay in the same form for all time? And there's a lot of scientific backup for this, this model, and the answer is no, it doesn't. But first of all, the bulk of it will simply be trapped by buoyancy, because CO2 is either a gas or a supercritical fluid. It's got low density, it will rise up and displace any other existing oil or water that's there. So that's one big hope. The other one is that some oil, beg your pardon, some carbon dioxide, when it's injected, because it's buoyant, it will stream away from the injection well. And it's recognized that little bits of it will be left behind as bubbles within the dominant fluid. And that's called residual CO2 trapping. It sounds a bit fantastical, but it's been shown experimentally and theoretically to work. So these are tiny bubbles of CO2 left behind in the dominant fluid, probably water. They're not connected, they won't flow, a bubble doesn't flow, so fluids only flow when they're connected. Then there's this one, this is solubility trapping. In my opinion, this one's quite controversial because this works on the assumption that the water that was there to start with isn't saturated with carbon dioxide. And I suspect that's not actually true, but nonetheless, let's work with this. So this is CO2 that dissolves in water or any remaining oil that sits in the porous rock. And we'll look at the solubility of CO2 in water in a few moments. And then this is the great white hope. This is mineral trapping, and this starts very slowly to begin with. Don't forget, this is a logarithmic scale. And then we're looking at what's about 30% of the CO2 will ultimately be converted into mineral form, which means it is immobile and will stay there forever. I'll talk a little more about that later, but this is what is assumed that will happen. Now, this is something, so I'll talk through this graph. There's a question, what happens if the CO2 leaks? And the simple fact is that if we spend all this money, time and effort injecting CO2 into the deep subsurface, and then somehow it leaks up to the surface, we need to know how much and how quickly. So somebody did a calculation of a large volume of CO2 injected into a structure, and then it leaks at 0.1% each year. Doesn't sound much, does it? Sounds like we should be able to cope with that. Well, the unfortunate fact is, after 2,000 years, we've leaked 90% of it, which means 90% of that greenhouse gas will have found its way to atmosphere. So basically, even a minuscule leakage will be catastrophic over long-range human timescales. Now, I think there's a tendency for people not to worry about, economists not to worry about 5 or 10 years' time, but we are now guardians of the earth, we always have been, in fact, and we need to think long-term. We need to think of many generations to come, rather than commit them to, well, what the fate I talked about with global warming and sea level rise and all the other problems. So we need to worry about leakage. So a quick couple of comments about a little bit of physics, actually. So what's the density of CO2? Because I've said when it's injected, it's going to be buoyant and it will rise up above any existing fluid. So something interesting happens when we push CO2 into the subsurface. It's a gas phase in the near surface, and then it changes into something called a supercritical phase, and there's a big change of density, but you can still see the gas, as you'd expect, has a low density, but even the supercritical phase CO2, which is neither gas nor liquid, it's that weird material in between, it's still got a much lower density than water. So even in the deeper subsurface, CO2 will rise relative to any water that's present. And again, that you weren't expecting to see phase diagrams today. But this is a phase diagram of carbon dioxide. This is temperature in degrees Kelvin versus pressure in bars. And this is CO2, and it will be injected at relatively low temperature, probably about quite close to zero, and also quite in the gas region down here. So that's about 100 meters depth equivalent. As CO2 is injected at increasing depths, then the pressure increases and you reach the critical point, and we end up in the phase that is a supercritical fluid. So it's neither gas nor liquid, it's in between, but we know that's still not a problem. It's going to be buoyant relative to water. A lot of people are worried about CO2 dissolving in water. They want it to happen. But there's some interesting things that need to be considered here as well. And one of the main ones is that CO2 solubility in water increases with increasing pressure. Now, every time you've opened a bottle of beer and heard those bubbles exsolve, you're reducing the pressure, and you're allowing the CO2 to come out of solution from the beer because you reduce the pressure. So it doesn't take much thinking to realize that elevated pressures lead to increased solubility of CO2, which is good because we are at about 100 bars or more in the deeper subsurface. So we are in a realm where we will start forcing the pressures to dissolve CO2. But there's also an issue of the salinity of the water. Now, these are in moles, and I've just converted these approximately into parts per million. Seawater has a salinity of 35,000 parts per million. Now, no one likes drinking seawater. Many oil fields easily have a salinity of 55,000 parts per million. Some of them are 220,000 parts per million. So if people inject CO2 into the oil fields offshore Liverpool, they are right down here. So there'll be much lower solubility of CO2 in this water in comparison to oil fields in the north part of the North Sea. So this is all important stuff that needs to be understood before we embark on CCS. So why do we think CCS will work? Well, there are many reasons actually, but first of all, whether people like to acknowledge this or not, CO2 has been injected into the subsurface for a long time, for at least 60 years, because it enhances oil recovery. So you inject CO2 into the edge of an oil field and you increase the fluid pressure, you might just simply push the oil to the producer well. But more significantly, when you inject CO2, it decreases the viscosity of oil, it makes it less sticky, and it increases the volume. So the oil will flow more and the volume will bulk up and little separated droplets of oil will reconnect and therefore be able to flow under a pressure regime. So adding CO2 to oil helps oil recovery. Now, you might say, and I've always thought that's counterproductive in terms of mitigating greenhouse gases. It is, but we know CCS can be done because it's been done a very long time. So interestingly, it was done first and foremost behind the Iron Curtain. Hungary, the Carpathian Basin, used it in the 1960s. And we know it can be done. And the CO2 stays in the subsurface if you want it to. Other reasons we think CCS will work is because people have already been doing it. The Norwegians, a company called Statoil, now changed its name to Equinor, have been doing it since 1994. So what they did is Sleipner field, which was operated by Statoil, it sits above the Heimdal Reservoir, and they recognized when they sampled this that the gas naturally has a large amount of CO2, which is useless. Traditionally, that would just be vented to atmosphere. Sounds horrific now, doesn't it? Huge quantities of megatons of CO2 just released to atmosphere because it's brought up to the surface. So what Statoil decided to do was take a more rigorous environmental approach, and they re-injected it into a much shallower aquifer called the Utsira Formation. And they have been monitoring it ever since 1994. So this is obviously a cartoon view. It looks like someone's down there, doesn't it? But this is the reality of what has happened. CO2 is injected at the base of the aquifer. It rises up. It hits something called an aquitard, or a thin mudstone layer. It finds its way through that one way or another because it's very thin. So we end up with like ponding underneath it, then it breaks through, it ponds underneath, breaks through. And we can recognize large quantities of CO2 are staying relatively close to the injection point, actually. So a lot of people were worried. You'll notice if you look very carefully that this is rising up. That's to the south, I think. It's rising up to the south. And the Utsira Formation actually outcrops on the seabed. Well, subcrops beneath the glacial till, in fact. But people were very worried that the CO2 in a gas would simply scream up the aquifer and bubble out at the seabed. It hasn't happened. It has not happened at all. And there's all sorts of mass balance and physics, and there've been enormous amounts of money spent monitoring this example. So CCS has already happened. Now, the difference between what we're trying in the UK now and this project is that in the UK, we are gathering industrially produced CO2 from cement works, steel works, power stations, gathering it and sending it offshore, whereas what Statoil did was simply separate the CO2 from the production fluids and then re-inject it locally. Still a valid thing to do, but the UK, what it's trying to do now, is actually much more ambitious, I'm pleased to say. So what can happen when CO2 is injected into the subsurface? So there's a range of scenarios, and I'll use a traffic light system here. Now, I'm a bit colorblind. I hope those colors work, green, amber, and red. So the green is good, the amber's not amazing, but it might be okay, and the red is bad. And I'm going to run through these. I'm going to give you some examples. So first of all, in terms of the good thing, that supercritical CO2 flows away from the injection well, no problems at all. Another good thing is that supercritical CO2 dissolves in formation water, creates an acid, which may then locally dissolve minerals. That's good too. Or alternatively, the CO2 may dissolve in water and lead to carbonate mineral growth. Now, those, the 2 and 3, sound like they're completely contradictory, and they are, but there's good explanatory reasons why that might be, as I'll talk to you in a few moments. Then we have 2 other things that are not ideal, but we can probably cope with. One is that the saline formation water, this is a strange bit of physics to think about, evaporates into the fluid CO2. The water leaves the brine, and the salt that's left behind as a salt crust blocks pores. Sounds fantastical. It definitely happens in saline fields. For instance, if it's done offshore Liverpool, the fields are so saline, the water's so saline, dissolving parts of the upper Triassic salts that we are familiar with, then we will have a halite blockage of pore throats due to this saline water evaporation. Another bad thing is that the high CO2 fluid pressure will weaken the rock near the wellbore, and it will almost certainly cause fracking, that dreadful concept that society now loathes so much. It will almost certainly happen. We have other problems as well. The elevated fluid pressure due to CO2 injection may well cause localized uplift of the rock on top of the CO2 injection site. Sounds fantastical, doesn't it? I'm going to show you an illustration where that has been shown. We could also have elevated fluid pressure due to CO2, which weakens pre-existing faults in the seal, and that will lead to earthquakes and risking rupturing faults and rapid escape of large volumes of CO2. That is a very profound worry. And then the last one might seem like where we shot ourselves in the foot, really, historically, but high pressure CO2 that flows in the aquifer, if it meets an unplugged oil well, then it will escape up to the surface. Now you might say, why would there be an unplugged oil well? And why don't we know where they all are? Well, unfortunately, records aren't perfect and engineers aren't perfect either. So records, we know, well, people have drilled development wells into existing structures and penetrated well bores that they didn't know were there because they hadn't logged their locality sufficiently. And we know that some oil fields leak through capped wells. Old oil fields with sub-economic quantities of oil are known to leak. We don't do it in this country. We haven't done it in this country, but it is known throughout the world. So of these scenarios, CO2 simply flows away from the injection well. What evidence do we have that this has happened? So I talked about the Sleipner project that's been going on for the last 26 years where CO2 has been injected. These are seismic slices through the subsurface on a repeat timescale, 1994, 1999, 2001, 2002. They stopped publishing them after then. There no reason, but it's just that Statoil were holding the information to themselves because they realized they were onto an economic advantage in terms of copyright and such like. Believe it or not, everyone needs to make money. So this is what happens when you inject CO2 into a previously water-filled aquifer. It develops density contrasts because CO2, remember, has a lower density than water. So all of a sudden, there's an added difference in density between aquifer and aquiclude, between thin mudstone layers and sandstone layers that are dominantly filled with CO2, because the bulk rock density has decreased. So we can image where the CO2 is, and we can see that that's where the CO2 has been injected, and we can see it's relatively localized. It isn't screaming to the left or right, it's just ponding beneath this top seal over, what's that, eight-year period. So that's fantastic. People have also processed the seismic and mapped it out, and they've mapped the plume over a similar time interval. That's before CO2 injection started. That's after 5 years, that's after 7 years. And you can see it is spreading out as you'd expect, but this movement is relatively slow. I don't have the volumes of CO2 injected here, but there's a very large amount of CO2 injected over that time period. Okay, scenario 2, CO2 dissolves in water and dissolves some minerals that are present. So does this really happen? Well, there's all sorts of reasons to expect this, and one of them is that nature shows us that this happens. So CO2 is a natural gas in the subsurface, and people have long studied natural CO2 accumulations and rocks that have been, if you like, motorways for CO2 moving around in the subsurface. That's natural CO2. What happens is that some minerals are soluble in mildly acidic solutions. So if you got some vinegar and put it on a block of limestone, what would happen? Of course, it would dissolve a little bit. Well, minerals in the subsurface are just the same as a slab of marble. If you put a mild acid on it, it will dissolve. So we did some experiments at Liverpool, and we took some samples that were bearing the mineral chlorite, which is an iron magnesium clay mineral, and it also contains siderite, which is iron carbonate. So this was a thin section of a sample before we did anything to it, and this is a thin section of a sample after we'd fluxed the sample with CO2 saturated water. So this is after, I think, not a long period, I think about a week. There's a short core plug, maybe an inch long, and we fluxed it very carefully. And you can see there are characteristics here that look very much like dissolution phenomena. And so a lot of the chlorite is gone, even the siderite is looking pitted. And interestingly, it looks like we've got some kaolinite here, which we didn't find in the previous sample. And that could be the product of dissolution of chlorite, and it's a chemical product of the acid effect on chlorite. So we have experimental data, and there's lots of other data to back this up as well, that some minerals may dissolve. The reservoir dissolving is one thing. The cap rock dissolving is something entirely different. And a lot of the focus that I've been involved in, research I've been involved in at Liverpool, working with Heriot-Watt University, Aberdeen University, and other universities around the UK actually, and Europe, Barcelona is a very important one. We've come to the conclusion that there are going to be different types of behavior depending on what type of shale or mudstone it is. And we've come up with different characteristics. So we've looked at a chlorite-rich mudstone, a non-reactive clay-rich mudstone, a calcite-rich mudstone, which people would call a marl, or a quartz silt-rich mudstone. And there are different types of behavior. So the yellow one and the red one, nothing will happen to them. If it's non-reactive or just bearing quartz, nothing will happen if you flux it with CO2. In contrast, the calcite-rich marl will start to dissolve, and you'll increase the matrix permeability, and you will probably decrease the risk of fracture permeability happening. Interestingly, you will increase the ductility, so it won't be as brittle. Similarly, chlorite-rich mudstones will also dissolve. So there's a new paradigm, there's a new thing we need to think about, and that is top seal mineralogy. That has become a very important way to categorize top seals on future CCS sites. Just a little bit of chemistry here. I want to explain why adding CO2 into the subsurface can do different things to the rock. And it all depends what other minerals are there. So if we add CO2 to water, the first thing that happens is it forms carbonic acid that then dissociates. And there's our H+, that's the acid. Now, if the acid encounters any carbonate minerals at all, it will dissolve them and simply increase the calcium. So that's called pH unbuffered. Now, because there's nothing to mop up the hydrogen apart from dissolving carbonate minerals. So let's go to the same reaction. CO2 reacting with water makes carbonic acid, which dissociates, makes acid. There's something else that can happen, that if you've got a lot of bicarbonate and a lot of divalent cations, that's metals in solution, the 2+ metals, they will react with the bicarbonate and make calcite. And both these reactions are making hydrogen, that's acid in the water. So this happens when we have a pH buffering system. And now that happens due to the presence, mostly feldspars, but also some clay minerals. And I've illustrated this for the clay mineral called chlorite, which is an iron, magnesium, aluminium rich clay. So what happens is clays like this, chlorite, mops up the acid and it reacts to make kaolinite and liberates iron and magnesium and quartz into solution. Now, if we go back to that previous diagram, we have a chlorite-rich sample here. And in this sample, the chlorite's dissolving and we've made kaolinite. So we are actually mimicking these changes in a laboratory, and this type of scheme is what is the key thing. So pH buffering or unbuffering is really, really important. And again, it means we need to look at the minerals that are present in the reservoir and in the topsoil. So what else can happen? Well, CO2 may well cause carbonate mineral growth, just like the equations I showed you before. And this has been shown again experimentally. So this is a lovely mineral called wollastonite, calcium silicate is a pyroxene. This is the before and that's the after it's reacted with CO2. No surprise, calcium silicate becomes calcium carbonate, and it will also liberate a little bit of silica. So this is what experiments show, but does nature show the same thing? Well, yes, it does, because we can look at reservoirs that are very rich, naturally rich in CO2, which also includes the Morecambe field just offshore, well, Lancashire, Cumbria, depending which way you want to look at it, have a very high CO2 content. And you can go and look at the minerals there and you will find lots of carbonate minerals. There are some slightly more weird carbonate minerals around the world that also result from CO2 in the subsurface. And this mineral, so that's quartz cement there. This mineral, this fibrous mineral, is something called Dorsonite. And Dorsonite is a sodium carbonate, effectively. It's got a weird formula, sodium aluminium hydroxycarbonate. It's like albite with a silicate replaced by carbonate. But we find this in the deep surface in reservoirs, and it is the absolute direct product of an natural influx of large quantities of CO2. So you bring CO2 into a system, you can cause mineral growth. Now that's the holy grail, but as you remember the early diagram, that may take 10,000 years or more. So the other thing that can happen, I mentioned that CO2 may cause halite to precipitate if the formation waters are very saline. So I'm not sure this diagram really helps. I've taken this from somebody else's work, but basically if you have saline water and you have dry carbon dioxide gas passing over it, the H2O evaporates from the brine and it will leave the salt behind. Now, as you leave the salt behind, it will reach halite precipitation and therefore grow halite. And this is after a first step. This is experimental work. This is the first step of halite precipitation due to CO2 evaporating the water. And this is after multiple steps. There's a major salt crust on this sample. And as you can imagine, that will block pore throats and limit permeability. And that might be really bad for injectivity of CO2. Very hard to deal with, in fact, but this is a problem we may have to encounter, may have to learn to deal with in due course. The excess CO2 pressure may well cause fracking. Now, fracking is only hydrofracturing. All we do is inject high pressure fluid and it splits natural weaknesses. And I've just shown you what a well bore with with hydraulic fracture running through it would actually look like. No scale on that one. You can see scale. This is obviously a cartoon. Now, fracking is an interesting thing, of course. I was born and raised in Blackpool, very familiar with the Preston New Road sites where companies have been trying to get shale gas out of the ground and basically failing due to public opinion. And I think when if the public were to learn that CCS is definitely going to cause fracking, there may be a reaction, and we need to be prepared for that as a community and need to counter it. Because fracking isn't that bad. It's only bad if fluids reach the surface, and there's no evidence that that would happen whatsoever. But nonetheless, fracking could happen. There are some short-term problems though, because if we frack the near wellbore region, we're going to damage the wellbore. Now that doesn't sound too bad, as long as we keep on injecting high pressure CO2. But what if we turn off the injectors over the summer when we're not burning as much fossil fuels? Then the borehole will simply collapse and we will ultimately lose injectivity. So it is a problem. And basically we need to plan to try to inject CO2 at fluid pressures just below the critical strength of the rock to try to avoid fracking as much as we can. So this needs to go in, this is called geomechanics. We need to go into this with very great deal of care. And we need to know the strength of the rock. We need to know the fluid we're going to be in, pressure we're injecting at. And we need to do experiments to work out maximum injectivity, because the faster we inject, the more financially and environmentally beneficial each well is. But if we pressure the CO2 too much, we will cause trouble. So I mentioned that injected CO2 might cause the land level to rise. Now that seems fantastical to me, but this is a project I was involved in the early part of the 21st century, through from about 2004 to 2012. This was the Kretschmer project, also known as the Insala Project. Kretschmer is the field, Insala is the CCS aspect to it in Algeria. And this was like the Sleipner case, that this was a gas reservoir in carboniferous rocks, and they recognized there was about 10% CO2 in the gas. And the idea was to mimic what Statoil had done at Sleipner and re-inject it, not in a deeper aquifer, because there isn't one. There's only the regional aquifer that people use at the margins of the Sahara Desert, of course, and the Algerian government would no way sanction that. But they did sanction injecting CO2 at the margins of the field they were exploiting. So that would have some benefits. They might even maintain pressure. CCS was associated with minor earthquakes, magnitude 1.7, which is way beyond our 0.5 permitted for fracking, for shale gas exploitation, of course. Much more worryingly for the authorities was that there was about 20 millimeters of uplift of the desert over 7 years of CO2 injection at the injection site. So this scale here, red represents uplift and blue represents collapse. These are the producer wells, these are the injector wells, and you can see local to each injector well, the land level rose about 20 millimeters, and in the producer wells, it dropped. This was described as a donut. It's not really a donut. It looks more like a strange footprint to me, but nonetheless. How could they do that? Well, this is the desert. This is right in the middle of the Sahara, where satellite imagery can measure or monitor land surface to within fractions of a millimeter. So it's sort of unfortunate for the operators that this was the case. If this was offshore, there's no way you could monitor that. If this was under vegetation with trees and grass, it would also be rather difficult to monitor. The sad news was that because of the perceived risk of rupturing the top seal, and the effect of that would be to contamination of the regional aquifer, that the Algerian government stopped it about 8 years ago. Even though there was no hard scientific reason to do it, they let fear drive them and the project was stopped. What else might happen then? So increasing fluid pressure may cause pre-existing fractures to fail. So not new fractures through fracking, but pre-existing fractures. And here's a Moore circle. I'm sure it's years since you've seen, or maybe not, I shouldn't patronize you. Maybe you see these all the time, and if you do, that's fantastic. What increasing fluid pressure does is it slides the Moore circle to the origin of a shear stress, normal stress graph, and we reach the zone of instability, the goes into the unstable zone here, and we will have slip at that point. So that's the pre-CO2 injection state. If we increase the fluid pressure, this Moore circle increases. That's the maximum principal stress, that's the minimum. It will move to the origin of the graph and we'll meet the region where there will be fracturing. Do we have evidence that this type of thing happens? Yes, of course we do. Every time you look at a fracture, natural fracture in an outcrop, this is the Kimmeridge Clay Formation down in Dorset. And you can see the fracture is picked out by the displacement of those dolomite bands there. And you can see there's a white mineralization. That's because it's cemented with calcite. And that cementation with calcite tells me that there's been fluid screaming up there. And then actually, in the end, the calcite will have blocked the fault, but there has been fluid movement up that fault. So if we have pre-existing faults that are close to being critically stressed, we increase the fluid pressure such that the fault becomes unstable, we may well cause movement on the fault and cause leakage, excuse me, of the fluids. So this is a very real risk. And again, we need to engineer this very carefully. We need to monitor how fluid pressure will vary. This means a lot of modeling work, in fact, to begin with. And we need to know about rock strength and the presence of faults. Now, seismic can image seismic scale faults. That's on the scale of maybe 20 meters of a minimum displacement, that is. But what about subseismic faults, ones that have 2, 3, 4, even 15 meters displacement? We don't know they're there. So it's very difficult to deal with. So people are trying to work hard using analogs of outcrops to come up with fault size distributions. So this is another thorny problem. What happens if the CO2 escapes from the aquifer via old, poorly plugged wells that penetrate deep into the reservoir? Well, that is bad news indeed. So this is what an old well should look like. So this is a very concertinaed view of the well. This may be going down, let's say, 10,000 feet, that sort of depth. There's the old production zone, and the oil field or gas field has run out of fluid. Normally, they would be blocked with a cement plug right near the reservoir. Points above it. This as the casing gets wider and wider, it will be plugged increasingly up towards the top. So it's not plugged once, it's plugged multiple times. And it isn't literally like a plug in the bath. It's like a plug in the water drain pipe below your bath, to draw the analogy. So you could say, well, surely that's fine, isn't it? Well, it would be if everyone plugged their wells perfectly, or even at all. Now, production wells will almost certainly be plugged, especially in our world, in Europe, North America, and so on. But what about exploration wells? Somebody's got a drilling rig, they've punched a hole in the ground, 10,000 feet, found nothing, no oil, no hydrocarbons. They thought, right, let's move on. We need to drill a new well, save money. And they haven't bothered doing the engineering side and plugging it, then that will be open. And even though water might simply be escaping up to this point, if CO2 is replacing the water, then you'll have CO2 escaping from that production zone. So that is a very real risk. So how much capacity is there for carbon capture and storage? Well, the answer is enormous, to tell you the truth. I came up with the estimate that based on a small number of fields in the UK continental shelf, we've got at least 200 years supply, but we could extend that because that's ignoring most of the biggest oil fields. In fact, we could exploit far, far more and probably go for orders of, well, maybe not an order of magnitude more than 200 years, but 2 or 3 times that. For the world, we have plenty of years of capacity at the current rate of production of fossil fuels. And that assumes all of the burnt fossil fuel exhaust gases are put down into the subsurface, which is by no means a certainty. But the good news is that we have huge capacity. The bad news is we are very slow at doing it. We have known we needed to do this for many years and almost nothing has happened. The UK has moved forward a bit, then back. The UK government has committed money, then drawn it back again repeatedly. We hope now we are on the inside track, and it is actually happening. There seems to be a vast change of attitude over the last 5 years, I would say, and it will happen in the UK, and it needs to ramp up. And that's not just 1 or 2 projects. We actually need hundreds of projects in the UK, hundreds of CCS sites. The other big problem is the legal and financial framework to make it viable, and public opinion, which is well beyond the realm of geoscience, but geoscientists need to get involved in that. I gave a talk at the Houses of Parliament about 2 years ago, just over 2 years ago, and it was on this Acorn project, the one that is now going to sanction, and there's going to be a CCS injection well drilled late next year. But the purpose of visiting Parliament with the engineers and scientists from the company I was working with on this project, we needed to get public opinion on our side. And the talk I gave, the audience wasn't made up of scientists, it was made up of journalists, chairmen of chair people of non-governmental organizations, MPs, senior civil servants, no scientists there whatsoever. And unfortunately, they are by far the most important audience because they control regulation and finance. And those are the people we need to get on side. Okay, I will stop there. Thank you very much for listening.
Fantastic.
Right. Well, that's quite a whistle-stop tour there, Richard, of some really important questions and concepts. At this point, I'd like to invite people to ask some questions if you're happy to take them.
Absolutely, no problem at all.
Yeah. Okay, so if anybody does have a question that they would like to give, you can use the raised hand on the reactions, and I will see you come up. You can put it into chat if you want to, or I haven't got everybody on the screen because we've got such a big audience this year, this month. So who would like to offer the first question for Richard?
There's a question that's come in from Jess to everyone, which I like. What role do you see for geologists in CCS? Yeah, that's interesting. That's an interesting question, actually. So geologists are needed for CCS just as they are for oil and gas exploitation, I would say. We need to know what's in the subsurface. I think the type of geologist is slightly different. So over the years, many petroleum geologists have basically been sedimentologists, applied sedimentologists, which nothing wrong with that. I think the change now is that for CCS, we need people who have a much greater understanding of geomechanics and structural geology. And that's speaking as a non-structural geologist by most of my research, but increasingly I'm working in the geomechanics realm, starting off by looking at relationships between, say, mineralogy and petrophysical properties in geomechanics. So I think there is a big role for geoscientists and geologists. There's also a lot of room for reservoir engineers. So these are people who work out what happens. Well, traditionally for getting oil and gas out the ground, they will build a simulation of an oil field, and they will simulate the positioning of production wells and injection wells and basically mimic the physics. Well, we can do the reverse, and that needs to be done. And geologists need to be involved in building those models. And probably the geology world and reservoir engineering world should merge together. That's my view. So I think geologists have a big need. That's my short answer. Somebody's asked if they can have the slides. The answer is yes. I will make them into a PDF and send them to Richard, who can circulate them.
Right.
Okay. Also, the talk has been recorded, and it will be appearing on the Westmoreland Geological Society YouTube channel very shortly, as are all our other talks from the winter series. So if there's anything that you missed or you didn't understand, you'll be able to catch up with that shortly.
So Richard, could you send me the web link to that when that happens, just for my own records?
I will do. Yep. Yep. Oh. So anyone else have a question for Richard?
Yes, I've got one. Tim Tranter here.
Hello, Tim.
Hi. Yeah, I was interested in you talking about those Liverpool Bay fields as being potentially poor candidates for CCS because of their salinity.
Well, that's not in their favour.
Right.
What is in their favour is they're very close to Connors Quay with existing infrastructure. So
yeah, because
they are being looked at very seriously.
Yeah, because I was going to say ENI have just got a carbon storage license, haven't they?
They have,
by the OGA last October. So okay, so there's other factors that could tip the scales in its favour, despite
Absolutely.
the salinity issue. Okay, it's not it's not necessarily a showstopper.
Let's hope it isn't. Put it that way.
Okay.
I am in conversation with Eni at the moment.
Right. Thank you.
Good question.
Richard, could I just ask you, on one of your slides when you were talking about the North Sea, you talked about the Captain Reservoir and how you would be injecting CO2 into that, but beyond the existing fields that are there. Now, I don't know whether those fields are full to spill structurally.
Yes, they were.
Okay, then how are you going to trap the CO2 if you go beyond the closing contours of those old fields? That's
a good question.
How do you know you have an up-dip seal?
That's a good question. Well, just like, so for the Utsira sandstone that Statoil are injecting into above the Sleipner field, that has a dip and it actually outcrops on the seabed, I think 200 kilometers to the south of where they're doing it. And there was worry that it would escape. But it's basically, the CO2's moved a couple of kilometers in 26 years. So the plume is rising up and it's not forming a very thin layer underneath the cap rock and running along. I think it's the physics of fluid flow in the subsurface is very much against mass leakage. And people have done long-term simulations. So there's some reservoir models. They're very difficult to do because there's a lot of assumptions needed. So most reservoir simulations work on probably a day time scale. You know, that's the repeat step. But we need to take things into the 10,000 year type time scale, and it makes the engineering modeling very difficult. But the assumptions that have been made and the models built show that for the Captain Sandstone, it doesn't really escape anywhere like as far as anyone might worry. It's nowhere near subcrop on the seabed or beneath I think there might be some young Cenozoic fine-grained sediments on the seabed at that point. But the modeling shows it's a long way. So the way to think about it is, how long does oil and gas migration take? Hundreds of millions of years in my experience. So I was once involved in a project in the Middle East, and there was a 200 million year time gap between the modeling estimate of oil and gas generation in the source rock and accumulation in the reservoir. Now, that's not quite the same thing as injecting at a point source, but as soon as you inject at a point source, the pressure will dissipate very quickly by cubic power law. So there will be a very rapid decrease in the driving force to move the CO2, in fact. So it'll rise up, but it isn't going to be screaming along particularly fast.
Okay. I just wonder how big an influence the reservoir type and the sedimentology has on that. Because I think the is probably a lot more permeable than the Captain from my experience.
So the Captain has an average porosity of about 25% and a permeability of about 2 darcies, if that means anything. So really highly porous and permeable, which makes it superb. It's a very, very good candidate. What I've realized is those very deep marginal reservoirs, let's think of the, say, lower Jurassic in the Central Graben, they're about 5 kilometers and maybe about 12–13% porosity. We don't need to go there, you know. In fact, the expense of injecting the CO2 to such a depth is prohibitive anyway, but the porosity is very poor. So, there's lots and lots of relatively young, relatively shallow aquifers that we can exploit, and including some older ones. So the Triassic, talk about Liverpool Bay again. So the Sherwood Sandstone offshore Liverpool Bay, I think the Lennox field is less than 1,000 meters below seabed, but it's got porosity of 25%. So it's a really good candidate, and that's a lower Triassic rock. So it's not age, it's depth that's the kind of way, and the burial history. But there's lots of good aquifers or reservoirs that we can exploit. We're not going to run out of those, not for a long time.
Okay. There's another question in the chat from Peter Morgan. How much energy is involved in the original?
Yeah, that's an interesting one, because there is definitely energy expended. I think I can't remember the name of the chemical process they use to separate the CO2. It's like a giant chemistry set, and that's in the realm of chemical engineering, not geoscience. I think it's called amine recycling. There is energy involved, but what's interesting is the companies who are planning to do this and those who are separating CO2 now on rigs ready for local re-injection are planning to do it using wind turbines. So they will be using a green form of energy. I know it sort of turns your head around that. I was having a conversation with someone from the company CNOC 2 days ago, and they are building floating platforms to provide power for their oil rigs, as opposed to burning some of their own products. There we go. I know.
Right. Oh. Oh, would anyone else like to ask Richard a question?
Well, I was going to ask one. It's Bernard Skillen de Bristow. I was involved in CO2 injection back in the 1970s with a European-funded project involving BP, IFP, CFP, and Alpha-Aquitaine. And as a result of that, BP proposed to capture and store CO2 from the Peterhead power station in the Bruce field. But that came to nothing because of the engineering problems of the capture side. So I'm wondering what the state of play of that is. And there are lots and lots of engineering problems that come to mind in doing that. I mean, amine separation of acid gases is age-old technology, but actually applying it to things like power stations is quite a different matter. We are talking about acid gases, so you've got problems of corrosion, particularly on pipelines. So can the existing pipelines actually be used to get the CO2 out to the fields? I'll leave it at that. There's lots of potential problems.
That's actually very interesting. I didn't know about the 1970s attempt. I'm going to go talk to my friends in the company that are organizing the Acorn project now to see if they know that. They might not. But Bernard, I might come back to you. I'll make a note of your name, because that's actually it's history, but it's a very interesting history. So in terms of the engineering, so CCS, it is happening, and separation of CO2 is happening. So whatever the engineering barriers were in the 1970s have been overcome. So that I think it's by scale, by innovation, in the realm of physics and chemistry. Like I said, that's beyond a geologist's knowledge area, but it does happen. It is happening. It has happened. So whatever the problems were, they've clearly been overcome. That's very interesting, though.
Well, there's another question, Richard, from Peter Morgan come up on the chat.
Oh, yeah. How does this compare with biological predictions? So I think it's the scale is where the difference lies. That the ability to remove large quantities of CO2 from industrial sources by this means is orders of magnitude bigger and faster than can be achieved by biological methods. I think biological methods might play a part, but I think there's a problem. And the other problem I've got conceptually is you grow a tree, that's great, it'll pull CO2 out of the atmosphere, and then the tree will die sometime when it falls over, and then it'll put the CO2 back. So it's a transient process. There again, I know enough about soil biology to know that we are losing organic carbon in our soil, so we need to reverse that process. So, the biological drawdown of CO2, we need it actually to feed us. Whether we can engineer that in the short term, I don't know. Whether it can be used as a CO2 mitigation strategy again, I don't know. One thing that is up and coming is this process called direct air capture, which sounds like science fiction to me, but people are moving forward on it. And this is where devices will draw air through them and remove those 400 parts per million of CO2. So they are planning to suck CO2 out of the air, called direct air capture. Some of that's a chemical process. Some of it is effectively artificial photosynthesis. So it's, if you like, artificial trees will be converting atmospheric CO2 into other materials. And again, this feels counterintuitive, but they are planning to make it into biofuels, which they will then burn and release the CO2 back to atmosphere. Whatever, I'm not in charge of the economics or the concept behind that, but these artificial trees or this direct air capture, people are taking it seriously. And again, that's out the realm of geology, but I know there are people at Liverpool University in our chemistry department and our Stevenson Research Institute who are actively working, doing research on this. So it's an area of active research.
Richard, have a question?
I've got my hand raised. Fred Owen.
Fred Owen? Go on, Fred.
You may be interested. I'm actually a retired chemical engineer, and I'm a member of the clean energy interest group. And today I received notification of a webinar on the Industrial Decarbonisation Challenge, which was set up in 2019. And that refers to the major research that's being done into carbon capture and storage and large-scale production of hydrogen. And that has been funded by like £200 million projects so far. And my question really is, I think that chemical engineers and geologists together could make an enormous contribution to all sorts of aspects of climate change, like thermal energy, heat pumps, carbon capture and storage, and hydrogen. And I wondered whether there's so many groups doing these things, how are they interlinked so that you're all sort of rowing in the same direction and using the resources and the skills that are available in this country to maximise the contribution that the UK to making these problems, get real solutions to these problems, because they're really enormous.
I completely agree. And I think, I don't want to use the word synergy, it's too much of a pop word, but working together is an ideal thing to do, and it should be done more. And it is slowly happening. So there's Liverpool University has a number of official research objectives or challenges, and there's one called Climate Futures, and I'm part of that. And the objective there is to try and bring people together from completely different disciplines to have overlapping research programs, ultimately to make a difference. So I recently put a bid in, working with social scientists, with people from planning, people from engineers from Heriot-Watt University, so not just Liverpool, in fact, really broad across the spectrum. Unfortunately, it wasn't funded. There again, most research bids aren't funded statistically, so you've got to brush yourself down and get on. But Fred, the sentiment is exactly right. We need to work together, and I think working together, educating each other, making each other see the limits to each other's disciplines and working out where there's overlap and where we need to potentially build new disciplines as well is the way forward.
Well, I've been pushing with the Chemical Engineer Institute of Chemical Engineers to get in touch with the Geologists of London to say, get to working groups working together to explore what can be done. But so far that's fallen on deaf ears as well. But,
interesting.
Yeah.
I'm surprised at that. Oh, yeah, maybe it's people protecting their own turf, not wanting to step outside their own comfort zone. There's normally people, in my experience.
Interestingly, the Greta Thunberg program the other night had a photograph of Trax Power Station where they had one of these, they have to scrub the CO2 out of the flue gas there. And they've got a pilot plant going there, testing the capacity and the getting data on scaling it up.
Very interesting. And I agree completely that it is needed.
Thank you.
Thank you very much. Good question. Good comment.
Can I come back in with a thought about fracking? Is it historical again? Back in the early days, the Forties field was the first oil field in the North Sea. And in the early days, that BP went to inordinate lengths with water injection to ensure that there wasn't any fracking in the wells. But eventually they realized that they were wasting their time, because A, you always get fracking in injection wells, which has happened more or less ever since the industry has been in existence. And B, that you actually need it to be able to get the injected fluid away from the wellbore. Because if you think about the wellbore, it's what, 7¼ inches diameter with a few holes punched in the side of the tubing. So you've got a very tiny area that the fluid's being pushed through. And the fracking produces a much larger area that the fluid can get away from. So it's really been proven that's to the advantage of it. Fracking, unfortunately, has got a very bad name. Unfortunately, people don't realise that BP was actually fracking wells onshore in the UK back in the 1950s.
Yeah.
It's not new technology.
No, it isn't at all. I always tell skeptical students, skeptical environmentally minded undergraduates that fracking isn't bad. It's been done repeatedly. Probably every oil field in the UK over the last 20 years has had fracked wells to improve production and maybe injection as well. So it's not new, you're quite right. It's just got a very bad press. It doesn't help that it's onshore as well, of course. It's underneath people's houses. And I think with the CCS project being offshore, maybe it will be much less of an issue.
Fracking was actually invented during the American Civil War by the water industry, not the oil industry.
Right, right.
Okay, well, I think that's a good selection of questions for you there, Richard. I don't know if any, one last chance, if anybody wants. And so I think it just leaves me to say thank you so much for giving your time and giving us a lecture on a topic which has become more and more topical in the news with all these different projects in Norway and hopefully in the UK. So we look forward to seeing you on the news explaining what's going on in Teesside or Liverpool Bay or wherever the first one in the UK will be. So on behalf of everyone, I'd like to say thank you very much again for an excellent lecture. Thank you.
Thank you.
Thank you.
Questions.
Thank you very much. Very good.